Hello and welcome back to Brad's class. The next couple of videos I'm going to talk about misconceptions, and the first one I'd like to go over is it would be easier to teach a student physics if they had no prior knowledge of the subject. Now, I'd like to take credit for this, but I heard this while I was doing some research on teaching a long time ago. So this isn't necessarily my idea. This is an idea I got from somebody else, but I just paraphrased it. In order to prove my point, I need you to feel something. So go ahead and look at this sign for a second. It's clearly obvious that this is a stop sign. It says stop. It's on the sign. If you see it, you should stop. However, it should feel like something's off. All right? You're not used to seeing it this way. In other words, even though the intent of the sign is perfectly fine, since it's not the way you're used to seeing it, it should create within you a feeling of something's wrong. Okay? Now, I want you to remember that feeling, because when we go over this, that is exactly the point I'm trying to make. So, whatever you felt initially when you were looking at this, just remember that feeling when we move on to the next part. Let's go over some chemistry. Now, whether you've had chemistry or not, I'm sure you have seen this stuff. This is the model of an atom. It has a nucleus, it has a proton and neutron within that nucleus, and it has an electron that moves around that central portion. Now, there was a very, very interesting experiment performed by Ernest Rutherford when he figured out that most of the mass was in the nucleus. All right. So this shows exactly that. You have protons and neutrons in the center. What you also see in this is that the electron circles around this nucleus because of positive and negative charges. So the protons have positive charges, the electrons have negative charges. So as far as what you need to know that the nucleus has the proton and neutron, it's in the center, and the electron goes around it. So this diagram's perfect for that. If you go through textbooks, most of them have something like this. Maybe not as fancy with the lines, but along those effects. When you learn it in chemistry, you learn it the same way. Diagram might be a little bit different, but it will be similar. This diagram is totally wrong. As far as scale and what things look like, this is not how an atom looks like. The concept is good, but it's totally wrong. Now, why don't students have a problem with this? Everyone knows this diagram. They're all fine with it. It's because no one's ever seen an atom. No one's ever seen a proton and an electron. All right? The fact of the matter is we don't really know what the shape of a proton is, or an electron for that matter. However, the mass of a proton is much, much greater than an electron. So there's no way that they'd be close to the same size. All right? The proton is roughly 1,855 times larger than the electron. So you can't see this on here. In fact, if we drew that to some sort of scale on here, you wouldn't even see that electron on this sheet of paper. The distance of that electron from the nucleus is also completely off. If the proton and the neutron nucleus was that big, that electron would once again be a couple miles away from this sheet of paper. So we couldn't effectively draw it. Now, why don't students have a problem with this? All right? You don't ever hear them going, well, that model is good for this, but it's not really realistic. The thing is you have nothing to compare it to. This is what you're taught. You don't see it in real life. Therefore, you think that it's true. You don't have any prior knowledge on this. Okay? And all the prior knowledge has probably been taught by teachers doing the same thing. How does this differ in physics? Well, I'm going to give you the statement. In the absence of air resistance, this feather and this hammer will hit the ground at the same time. Once again, we're assuming that they are dropped at the same time, and we're assuming that there's no air resistance, and we're assuming that they're at the same height. Okay? Now, first thing you should be doing is the same thing as a stop sign. You should be going, that is not true. Why is that not true? Everybody knows what a feather is. Everybody knows what a hammer is. And everyone has seen what happens when a lighter object and a heavier object are dropped at the same time. So you have prior knowledge to this. So that prior knowledge kicks in and you go, that can't be true. All right. Now, the thing about this is how easily are you able to change your mind? And that's what really physics is about, because when we teach physics, we're teaching about things that a student or person always sees. So they already have a built-in conception or misconception on why something happens. So as I walk you through this process, find out for yourself, what part do you believe? What part are you willing to change your mind on based on the evidence? And what part do you still not believe after I've finished explaining it? Because that is critical to learning physics. All right, let's go through a couple points and see where you are in your understanding. The first point, there's only one force on these two objects because I stated that there is no air resistance. So it is gravity. Gravity accelerates everything at 10 meters per second squared. That means that for every second, the object would increase their speed by 10 meters per second. So let's say both of these objects start at 0 speed. Once we drop them after the first second, they would be moving at 10 meters per second. After the second second, they would be moving at 20 meters per second. So let's say it took 2 seconds to reach the ground. They would not only fall at the same time and hit the ground at the same time, they'd also have the same velocity or speed when they hit the ground. How'd you do on that? Does that make sense, or do you still not quite believe it? Let's go into this a little bit further. I said that ignoring air resistance, we just have the force of gravity. There's actually an equation for this. The force of gravity is equal to mass times the acceleration. Now, we know that mass, or the amount of matter in something, is different in these two cases. In other words, the hammer has more mass than the feather. Okay? So, how can they both hit the ground at the same time and at the same speed? So let's look at this equation. The force of gravity and mass are directly related. In other words, when the force of gravity increases, the mass also increases. When the mass decreases, the force of gravity decreases. Now, let's think about this. The lighter object, which is the feather in this case, has less mass. So the force of gravity to move that would be less. Let's look at the hammer. The hammer has more mass, therefore the force of gravity would have to be greater. So let's give you some numbers and see what happens. All right, we've given some numbers for the feather and the hammer. We're going to say that the feather has a mass of 0.1 kilograms. We're going to say that the hammer, which is heavier, has a mass of 1 kilogram. So we know that the lighter object, the feather, is going to take less force to move it, which is 1 Newton in this case. So 1 Newton divided by 0.1 gives us 10, which is the acceleration. Now we have the hammer at 1 kilogram. It has more mass than the feather, therefore it requires more force to move it, which is 10 newtons. However, when we divide that proportion, we still get 10, which is also the acceleration. So the feather requires less force because it has less mass. The hammer requires more force because it has more mass. But when you do the proportion, they both come out to the acceleration due to gravity of 10 meters per second squared. Now I've given you two reasons why those two objects hit the ground at the same time. Do either of those make sense yet? All right, here's the final piece of evidence. This is one of the first experiments that they did when they landed on the moon.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got the...
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
I always imagine what would happen if it hadn't actually worked up there. But anyways, I've given you some clear indication of why this happens. And here's the key. You've seen this happen before. Lighter objects take longer. It's because of air resistance. But the thing is were you able to take the evidence that I gave you and adjust the way you think based off of that? Especially if you didn't understand the concepts, definitely seeing that video. So, I hope I proved my point that physics isn't about necessarily learning difficult concepts. It's about looking at things a different way and how willing the student or the person is to be able to change their mind based off of evidence. That's all for today. Thanks for watching.